answer them. And you can hear me well, right?
Yep, yes. Thank you.
Okay. Yeah, so here the client has small local storage, so it outsources storage of its memory to an external server. However, this outsourced storage might contain sensitive information, which the client wants to hide, and it's not enough just to encrypt the outsourced memory. For instance, the client may be a hospital that has outsourced patient records, and these records might be sorted and grouped by age. So in this scenario, shown on this slide, the server sees that a record of an elderly person is being accessed, and this leaks sensitive information. So it's important to also hide access patterns. And to do this, Oblivious RAM presents a solution. So before we understand what Oblivious RAM is, let's first formally understand what RAM is. So RAM, or a random access machine, allows you to access memory using two instructions. The first that lets you write values to some specified address in memory, and the second that allows you to read some specified address to fetch the value that was written to it. An Oblivious RAM can be thought of as a compiler that is some code run by the client that takes as input some RAM instructions, which are reads and writes. So here the triangles are reads, and these squares are writes, and these circles are some values that are returned back as data for every read that is issued. So the compiler takes as input some RAM instructions and compiles these to further RAM instructions that are sent to the server, such that the server, when it sees these compiled RAM instructions, learns nothing more than the number of original RAM instructions. So here the server only learns that 5 RAM instructions were issued. It doesn't learn whether the instruction was a read or a write. It doesn't learn what addresses were accessed, and also doesn't learn what values are returned for every read. So formally, we define a security using a simulator. If it's possible to construct a simulator that takes in the leakage, which is the number of RAM instructions, such that the simulator is able to simulate a view that is statistically indistinguishable from the real view that the server sees when it interacts with the compiler in the real world, then your ORAM is secure. And intuitively, this because you're able to simulate the same view while having as input much less than what is originally learned. So ORAM schemes are usually evaluated using two metrics. The first is blow up, which is the number of compiled RAM instructions that are sent per original RAM instruction. And the second is the number of rounds, which is the back and forth interactions that the compiler makes with the server. Existing ORAM schemes achieve optimal blow-up or optimal rounds, but don't simultaneously achieve both. So it is known that a log n blow-up is required for ORAM, where n is the size of the outsourced memory. And Optorama is such an optimal ORAM scheme that does achieve this blow-up. However, the hidden constants for Optorama are too large, and Optorama is impractical. The more practical path ORAM incurs a suboptimal blow-up, and the ORAM scheme that requires just a single round incurs much worse blow-up. So a natural question to ask is, can we have the best of both of these worlds? Can we have an ORAM scheme that requires just a single round of interaction and incurs optimal blow-up while having small client storage? And unfortunately, the answer to this question is no. There's a lower bound that says that any one-round ORAM scheme must incur root and blow-up or root and clients or require root and client storage. So what can we do to get around this lower bound? What we do is we propose a new model of computation in which lower bound does not. Yes?
Isn't the square root ORAM you're listing better than that? You're listing square root ORAM as having log cubed bandwidth blow up?
Oh, this is not square root. This is SR ORAM. It's something different.
Right, but okay, isn't SR ORAM beating the cache result? Because it has one round and log cubed bandwidth blow up.
Oh, I see. Okay. So this lower bound applies for ORAM schemes that don't use cryptography. But the SR ORAM uses, no, sorry, don't use cryptography, where the server is not allowed to perform computation. So the server just acts as a black box for storage. You can only perform reads and writes. It's like a balls and bins server.
Okay.
But the SRORAM scheme to achieve this log cube and blow up and one round, I think it requires the server to perform some computation, maybe XOR or not XOR, not simply XOR. I think
Yeah.
it needs to perform some homomorphic encryption computation, which this um, lower bound only applies when the server is not allowed to perform computation.
So when the server just has like sequences, like is an array.
Yeah, the server is simply an array. Yeah.
Thank you.
Okay, shall I continue? I'll continue.
Yeah, please.
So our main goal is to get more efficient oblivious algorithms than what we can achieve using general purpose ORAM. And to do this, we first propose a new model of computation called a single access machine and construct an oblivious single access machine that is somewhat analogous to an oblivious random access machine, but is more efficient than existing oblivious random access machine constructions. Then using our OSAM, I'll call this OSAM from now on, we construct what we call a smart pointers interface. That this interface is very similar to any pointer interface that you're familiar with when you're using pointers at C++ or Java, but they additionally guarantee obliviousness, which means that when you dereference a pointer, the server does not learn the location that is being dereferenced. And using smart pointers, we obtain more efficient oblivious algorithms. So now I'll explain what our single access machine interface is, what an oblivious single access machine is, and then I'll explain the interface for our smart pointers. And after that, we will look at how we construct an oblivious single access machine and how we can use that to construct smart pointers. And finally, a high level intuition of how we can get more efficient oblivious algorithms. Okay, so a single access machine is similar to a random access machine, except that there are two restrictions. So first is that any address that is written to or read from must be allocated beforehand by some pre-specified alloc instructions. So in addition to write and read instructions, we also have an alloc instruction that has to be implemented by the single access machine. And the second and more important restriction is that every address must be written to at most once and read from at most once, which is why we call it a single access machine. Just like ORAM, OSAM can also be thought of as a compiler that is some code run on the client that takes as input some SAM single access machine instructions, one of these three, and compiles them to RAM instructions that are sent to the server, such that the server learns only the number of non-alloc operations. So it learns the number of reads plus writes. And here, if these stars are alloc operations, it learns that 5 read plus write instructions were issued, but it still doesn't learn which was a read and which was a write. And similar to our security notion for, yes?
So just to,
Sorry, can you hear Amir?
I can hear.
okay, so the server does not learn the number of alloc operations.
Yeah, the alloc operation it's sort of something which is more internal to the client, and the server only learns the number of read plus writes.
So, okay, so I guess follow on for that. How could you possibly hope for that? So if I do alloc of like 2 to the 60 addresses, I guess I'm storing them all locally because the server's not seeing anything.
Oh, yeah, I guess if you want small client storage, then you'll probably have to, you can maybe alloc, and then you will not, if you choose not to use those addresses, then you don't have to store them on the client. Otherwise, you can allocate addresses and maybe store them on the server, but the server will not learn that an alloc instruction has been issued.
I think, if I may, Am I correct to say that the alloc operation is not really requiring the server to allocate storage? Like if your server does not have storage for your 2 terabytes that Ben wants to allocate suddenly, then nothing will happen. I mean, yes, you have allocated 2 terabytes and the server does not have 2 terabytes for you, but I mean, nobody knows about it until you try to write the 2 terabytes, in which case I guess there will be, in practice, of course, there will be a problem. But the alloc operation is not really what we usually think about allocating memory. It's not really allocating, it's just telling the algorithm, I guess, okay, now I'm allowed to do a write operation, read operation from these addresses, correct?
Yeah, I think so. I couldn't hear you very well, but I believe that what you're saying is true. So maybe I'll just add on to that. The server's memory, the amount of memory that is on the server is fixed in advance. So alloc is not creating new memory for you to write content to the server. Instead, yeah, it's just saying that if you have to write some content to some address, that address cannot be specified by you, but instead must be specified by this alloc algorithm. So
But it is reasonable that the client could have storage that scales with like, right, if I alloc a bunch of addresses and I'm not managing them in some other way, the client needs to know, here's the set of allowed addresses I can write to. Right, so you need a way of like managing the set of alloc addresses by either writing them to some other address
Yeah.
or something else. Okay.
yeah, that's true. That's true. So the client needs to somehow know that these are the only addresses that it can use. And so, yeah, that's true. It will either have to write those addresses back to the server somehow or store a few of them in its memory. But yeah, it must be kept in mind that the client's memory is small in size.
Another question?
Sorry, speak up a little bit.
Yes, another question. These awesome machines, do you actually, are they general computing machines? Can you compute and understand these awesome things? Are these Turing machines?
Oh,
Right.
sorry, can you repeat that?
Can you express every computation as a
Oh.
computation?
So we show that you can express RAM using, you can compile a random access machine to a single access machine. And since a RAM is Turing complete, then so is SAM. But there'll be some extra cost in compiling. There's a log n cost in compiling any RAM program to a SAM program.
Okay, good. Thank you.
Okay, I'll continue. So yeah, similar to RAM, to show that your SAM is secure, you'll have to construct a simulator that takes in the leakage, which is the number of read plus write instructions, and should be able to simulate a view that is statistically indistinguishable from the view that the server sees when it interacts with the OSAM in the real world. Okay, so to better understand the SAM model, let's look at some examples. These are pretty simple, but then it'll just help understand exactly what the model is. So do you think this SAM program is valid in the sense that it respects those two restrictions that we had? The first restriction is that every address must be allocated beforehand, and the second is that addresses can be written to at most once and read from at most once.
No.
Yeah, that's the right answer. So why no?
There's no alloc.
Yeah, that's true. Okay, so you'll have to alloc an address before you can use it. So this is the right program. Okay, is this program correct?
No, because you can do it once.
Yeah.
One
So
read.
yeah, this is incorrect because you're both reading and writing the same address twice, and so it disrespects the second restriction. However, this does raise an issue. If you want to repeatedly read the same value, then how would you do it? You cannot read the same address, right? So how you would try to repeatedly read the same value is, first, you will allocate one address, maybe write it to that address and read that address to fetch the value. But if you want to fetch the value multiple times, so you'll have to allocate a second address and write the value to that second address and read the second address. So somehow, if you want to fetch a value multiple times, you'll have to keep track of what allocated address the value currently resides in. And a lot of our work actually goes into just figuring out how this can be done efficiently. So this is the right program. And this is a little subtle. So do you think this one is a valid SAM program? So here I'm allocating an address and directly reading from it without ever having written to it.
Yes.
Yeah, that's true. So it is valid. It seems a little counterintuitive, but it does respect both our restrictions because we are allocating the address beforehand and we are not reading it more than once. So in this case, when you read an address that has not been written to, we assume that a special none symbol has to be returned. And we will actually use this fact to construct our Oblivious smart pointers. So yeah, now we saw, are there any questions until this point? Okay, I'll move on. So now that we saw what the SAM model is, let's look at the interface of the pointer, smart pointers that we achieve. So we build these following smart pointers interface using as SAM programs. You can write some new value to memory and get a pointer that points to that value. You can use a pointer to fetch using this get instruction, the value that the pointer is pointing to. You can use a pointer to update the value that a pointer is pointing to. So now it's been updated to some new value val prime. And you can copy a pointer to create multiple pointers that are pointing to the same value. And you can also delete pointers. So our interface gives these 5 different operations. And using this, we show in our paper that you can construct multiple data structures that are as efficient as prior work or better. And we show that you can get doubly linked lists, play trees, tries, and a bunch of graph algorithms. So more specifically, we get these following results. First, we construct an OSAM that does achieve a blowup of log_n and requires a single round. And this log_n blowup is optimal, so it's required. And using our OSAM construction, we design this smart pointers interface that I described just now with an order log_d, log_n blowup, and log_d rounds, where d is the number of shared pointers that point to the same value. And using our smart pointers, we get 2 new results. The first is a caching ORAM. With this cost, and I won't go too much into the details, but this t is at most log_n, and it's in many times a small constant when you frequently access the same value, which is why it behaves like a caching ORAM. And so this ORAM is never worse than path ORAM asymptotically, but in many cases it's better. And we also give multiple graph algorithms, breadth first search, depth first search, single source, shortest path, and minimum spanning tree algorithms with this cost, where E is the set of edges in the graph. And I want to point out that our algorithms for SSSP and MST are almost as good as the non-oblivious versions, which means that it does not cost you anything asymptotically to get oblivious algorithms for single source, shortest path, and minimum spanning tree.
And sorry, so this, when your bandwidth blowup in rounds is dependent on D and T, those are considered public parameters now of the computation?
No, so D is, in many cases, let's consider that you're outsourcing, the client has outsourced some graph to the server, and the client wants to hide the structure of the graph, right? That's one of the purposes of ORAM, that we want to hide access pattern. So we want to hide the degree of nodes in the graph. This D is not revealed to the server. It's not public information, but the cost of the entire graph algorithm will depend on not these graph algorithms, but if you're using some generic, maybe random walk or something, then that cost of traversing an edge to a node that has d number of incoming edges will scale with log d. And
So,
what is revealed to,
how can I have a thing where the number of rounds depends on a private parameter?
yeah, so what is revealed to the server is the total length of your graph program. So if maybe you're traversing a path that is of length 100, and each node on this path has varying degrees, then the total length of total log d log n is revealed, but not the individual log d values.
Okay. Thank you.
Mm. Okay, I will continue. So now we will look at how we construct our OSAM, and then we will look at how we construct our smart pointers. So our OSAM construction is based on path ORAM. So let's first have a high-level intuition of, let's look at the key ideas behind path ORAM so that we can understand how our OSAM construction works. So in path ORAM, the client, wait, is everyone familiar with path ORAM?
No.
Okay, I'm gonna explain. So in path ORAM, the client outsources, the outsourced memory that the client outsources to the server is structured as a tree, and all the data that the client outsources is stored encrypted on this tree, such that every RAM address is mapped to some uniformly random leaf in this tree. And this mapping is called the position map. And for now, let's assume that it's stored on the client. So here, what this means is that the value written to address 1 lies, path ORAM maintains this invariant that any value written to some address will lie on the path from the root to the leaf that it has been mapped to. So here the value written to address 1 lies somewhere on the path from the root to the third leaf. So when the client issues a read request for address 1, the ORAM compiler will look up this position map and see that 1 is mapped to 3. So it will ask the server to fetch the path to the third leaf, and the server will look this up and return this to the compiler. Now, all the contents in this path are encrypted, so the ORAM will decrypt all these values and figure out which one the client wants and return that back to the client. So now that an access has been made to this address, if the client wishes to access this address a second time, it's not okay to reveal the same path to the server, as the server will see that the same address is being accessed twice, and even this frequency leakage can leak sensitive data. So every time some address is accessed, we will sample a fresh uniformly random path that it will be rewritten to the server. So now that we accessed 1, we flip some coins, we sample a new leaf, and that turns out to be 4. So the compiler will issue a request to the server to write this value back to the path to the 4th leaf. And now I'm going to hide some details from you, but this is done in such a way that the server doesn't learn that this value is written to the path to the 4th leaf. It just learns that it doesn't learn anything. So the server learns what paths are being read, but doesn't learn what paths these values are being rewritten to every time an access is made. So at a high level, all that the server sees is that some uniformly random leaves are being accessed every time some instruction is issued, and that's why we can simulate a view of the server. So now if the client requests to read the same address a second time, the compiler will look at the position map, see that 1 is mapped to 4, and ask the server to return the path to the 4th leaf. And this path is returned and decrypted, and the value is returned back to the client. So there is a problem with this construction, and the problem is that this position map is too large to be stored on the client. It's of size n, and we want the client storage to be much smaller. So how path-ORM gets around this problem is to recursively store this position map in smaller trees on the server. And every time some path, if you want to figure out what uniformly random leaf a path is mapped to, you will have to first look at the smallest tree and then look at the next smallest tree and so on until you get the path that you want and can look that up from the largest tree. So this is a bit tedious, but at a high level, what you can take away is that there will be log n levels of recursion. And in each level of recursion, you will be reading a path that is at most of size log n. So that's why the total blow-up is log square n for path ORM. So our OSAM construction is basically path ORM without these levels of recursion. And we look at why this is not required for OSAM. So recall that in OSAM, before any address is accessed, it has to be first allocated. So if the client issues an alloc instruction to the compiler will sample some leaf uniformly at random and append to it a counter that is some increment that is incremented every time an alloc instruction is issued, and it will return this as the address back to the client. Then if the client wants to write some value to this address, the compiler, OSAM compiler, will strip off the leaf from this address and it will write this value to this leaf using that magic algorithm that somehow hides from the server which leaf the value is being written to, on like the path to which the value is being written to. And then when a read is performed, the compiler will strip off the leaf from the address and it will issue the request to the server to read the path to that leaf. The server will respond with that path and thus the compiler can return the value required. So now why is there no need for a position map? This is simply because OSAM is much more restrictive. We know in advance that every address is read at most once, and also every address must be freshly allocated. So the problem we had with ORAM was that an address could be read multiple times, and that's why you would have to have the position map to figure out the new leaves that an address is remapped to every time it is accessed. But here, we know in advance that every address will be accessed only once, so there's no need to have the position map and all those log n levels of recursion. So here as well, all the server sees is some uniformly random leaf being accessed every time, and that's why it's possible to simulate the view of the server. So I know this went a bit fast, but is at least the intuition behind how OSAM works okay? Or
So you allocate this pointer when you do alloc, and then you never use it.
a pointer?
Or sorry, the counter.
Oh, the counter. Yeah, the counter is only used to ensure that an address is unique. So it sort of acts like an identifier for some value. And then when you read, when you do this read path instruction, you can look for the address, which is a leaf along with the counter, which will definitely be unique for every value that is written. And you can use this combination to figure out that this is the value that the client is looking for.
Okay, so two addresses could currently point to the same leaf. So
Yeah, that's true.
I could read the same leaf multiple times over and over.
Yeah, that's true.
Okay.
But if those two addresses do happen to be at the same leaf, then that's because you uniformly chose that leaf for both the addresses, so it's not going to leak anything.
Yeah.
Okay, so even if you did not understand this, it's fine, because the rest of the talk actually does not rely on this. So now we will look at how we construct our smart pointers. And to do this, all we'll have to do is we will have to implement those 5 instructions as SAM programs that respect those 2 restrictions. And we know that SAM programs that are valid and that respect those 2 restrictions can be compiled to Oblivious programs. And then we are done. We get our Oblivious pointers. So first we look at the intuition for how we can construct pointers for trees, and then look at how we can construct them for the more general case of graphs. So say that the client has outsourced this potentially unbalanced tree to the server, and this box, this dotted rectangular box at the top, is the client's local memory that, bear in mind, is small in size. So initially, the client stores an address to the root of the tree, and every node on the tree stores addresses of the left and right children. So as the client reads this path, since we are in the single access machine model, since all these addresses have been read, they cannot be read again. So the client is burning down this path as it reads it. So it will have to allocate new addresses for these nodes, make sure that the nodes are written to those new addresses, and make sure that the parents are updated with the new addresses of their children. So we'll see how that happens. So the client can use the first address that it stores to fetch 1, which is the root. And here the old address of 1 is invalid. So we will allocate a new address for 1. And before we can write 1 back there, we'll use 1 to fetch 2. And here as well, 2's old address is invalid, cannot be used again. So we will allocate a new address in advance for 2. Make sure that 1 points to this new address because we will have to rebuild the tree. And now we can write 1 back, clearing it from memory. So here on the right is the SAM program that we will be using to traverse this path. So we can continue doing this. We can use 2 to fetch 3. And the old address of 3 is invalid. So we will allocate a new address for 3, make sure that 2 points to this new address. And now we're done with updating 2, so we can write 2 back. And this can continue until the client reads the whole path, which may be of arbitrary length, but all the time the client will keep writing things back, so we'll only have to keep a constant number of things in its local memory. However, this technique does not work for graphs, and we'll understand why with an example. So say that we have this case and we want to traverse this edge from 1 to 3. Then just as with trees, once we read the address of 3, we will have to rewrite it to some new address in order to rebuild this edge. But the moment we write 3 to some new address, 2 still has the old address of 3 and has not been updated. But our algorithm did not require that we have to traverse this edge from 2 to 3, and so we could not update 2. Now you might think maybe we can have some backward pointer to 2 to somehow update 2 with the new address of 3. But if you want to do that, you will have to read 2. And in that process, you'll also have to move 2 to some new address. But 2 may have some further nodes pointing to it. And those nodes will now be pointing to some invalid address. So this effect might ripple over the entire graph, and you might have to update the entire graph, which is just too expensive. So there must be some way for values to update pointers that are pointing to them with their new addresses whenever they are rewritten to some new address. So are there any questions up till this point? Okay, I will continue. So in order to be able to do this, we'll first construct, as a SAM program, a queue. And the queues, so first I'll explain the queue's interface, and then we'll look at how we can construct the queue as a SAM program. So it's very similar to any queue that you're familiar with. We can have an initialize queue instruction that returns a head and tail pointer. Then we can add values to the queue using the tail and using an enqueue instruction. So every time you enqueue a value using a tail, you will be returned a new tail that you can use to enqueue further values to the queue. So here we enqueued some value v1. You can use this new tail that was returned to enqueue a second value v2. You will be returned once again with a new tail, and you can keep using this tail to enqueue further values. Then you can use the dequeue instruction to read values from the using the head of the queue. So a queue is a first in, first out data structure. You will first read the value that was first enqueued. So we will use head to read V1, and similar to enqueue, you'll be returned with a new head that can be used to read subsequent values. So you can use your new head to read the next value and so on. So note that here, every block in the queue points to the next block in the queue, which is how you can update the head. Finally, the head will catch up to the tail, and at this point, the queue is destroyed and it's empty. So let's think about how we can implement this queue. So anyone has any ideas for how we can implement this init queue operation? What kind of SAM instructions do we need?
So I want to allocate an address, but I'm going to have 2 pointers to it, which you just told me was bad. But I am going to allocate an address.
Yeah, that's true. So all you have to do is you just have to use alloc. And then here both head and tail are initially pointing to the same value. So you can copy you can allocate an address, say that's assigned to head, and then you can just copy the value that was assigned to head to tail, and you can return this. So that's how we can implement init queue. Now, how can we implement enqueue?
So
Here
that's just a right to tail. And that, or it's an alloc of a new tail, and then it's a right to tail.
Yeah, that's true. So so mainly you have to write this value to this tail, but you have to be a little careful because we also need to ensure that every block points to the next block in the queue. And the next block will be the new tail that is returned. So you'll have to first allocate the new tail, and then you can write the value along with the new tail to the old tail. So you're writing this block. You've allocated this new tail, and then you're writing this along with the value to the old tail. And then you can return a new tail. So here, this alloc procedure helps us because you're able to allocate addresses in advance before you actually write to them. Now, finally, how can we implement the dequeue instruction?
Read the head of the queue.
Yeah, that's right. So all you have to do is just read the head. But there is a small corner case. That is the case when head and tail both point to the same location. And this is the case when the queue is empty. So in this case, remember that when you read an address that has not been written to, you are returned a special none symbol. And this is where it helps for us. So in this case, we can return null instead of returning the actual value stored there. And this can be used to tell maybe some higher level program that invokes the queue that the end of the queue has been reached. And this will be useful in constructing our smart pointers. Okay, so now that we have this queue, let's look at how we can dereference a pointer. So instead of making the pointer just store an address of V, we will make the pointer store the head of a queue that stores all the addresses that we moved to since this pointer was last dereferenced. So every time V is rewritten to some new address, maybe because it has some other pointer that points to it, it will append that address to this queue using an enqueue operation. So the value holds the tail of the queue, using which it can perform this enqueue. And then later when this pointer is dereferenced, we can use the head of the queue to keep dequeuing the queue. So first I'll read the first block, then the second block using the head, then the third block, until we reach the end of the queue. And we know that the latest address of the value will always be the last address stored on the queue. So we can use the address stored in this block to fetch the value. So let's see, maybe it helps to see when you have two pointers pointing to the same value. So this was the issue that we had previously when we had two nodes 1 and 2 pointing to the same node 3. In this case, let's say that we dereference pointer P1. So here we will traverse this queue until the end and use the address stored in the last block in the queue to fetch the value V. This point V moves to a new address, and this is enqueued to this other queue that P2 points to. And let's say that we again dereference P1. So we will once again traverse this queue until we reach the end and use the address stored in the last but one block to fetch the value. And once again, the value moves to a new address, and this is enqueued to this queue. Now, when we dereference P2, we will skip the old addresses of V and go and dequeue this queue until we reach the end. And then we can use the latest address stored in the last block in the queue to fetch the value V. So this is how we overcome the problem that we had previously. So I'm going a bit fast. Are things okay?
So I see how V has to, right, so you're looking for like D accesses here. I see how V has to keep 2 pointers to queues, but couldn't those queues be of unbounded length? Right, if I move V a whole bunch of times.
Yeah, that's true. So this queue could be of unbounded length, but we can show that the amortized cost of any dereference will be a constant if V has a constant number of pointers pointing to it, because you can charge in advance for every time you do an NQ, you charge in advance for the DQ. So normally the NQ operation would just cost one write, but let's charge in advance for the read. So say that it costs 2 instead, then the DQ comes for free, and therefore the overall cost will be constant. But all of this is only in the case when the value has a constant number of pointers pointing to it.
And I guess, is it possible to do an amortized like cleanup? I guess because you have no idea how long any of these queues are. So the only way you could do it is like to read the whole graph and do, right? Like you don't have any sense of how long the queues currently are.
Yeah, I think it is possible to do an amortized cleanup. So maybe if you want the queue to only be of, like once the queue's length reaches some fixed value, let's say 5, then I know for if every value has only 2 pointers pointing to it, then every time it is accessed, this value can keep track of the size of the other queue. And when it exceeds that length, if the value also stores the head of the queue, it can do a cleanup. So in this implementation, only the pointers store the head of the queue. If you want to do a cleanup, you can maybe have the value also store the head of the queue and then read through it every time some certain length is reached. But yeah, you'll have to carefully figure out the amortized analysis to ensure that at least practically it's not too expensive. Because I have sort of tried this for some other, for something else that we were working on, and the amortized analysis is a little bit tricky, and this turns out to be expensive. Okay, so I'll continue. I'm just realizing that maybe I'm a bit short on time, but there's not too much left. So now let's look at how we can get our smart pointer interface using these queues. So a new instruction is simply just an initialize queue instruction to create a new queue. Then you will have to return the head as the pointer and write the tail to the value. And also you just have to make sure that you enqueue the new address that you're writing the value to this queue that is initialized. Then a get instruction can be used to read this queue until the end. And then you can use the last address stored on the queue to fetch the value. And also you will rewrite the value to some new address, initialize a new queue, and enqueue that new address to this queue. A put is similar to the get. You will, let's say that we do a put on this pointer, you will read the queue until the end, use the last address to fetch the value, and then update the value. So when you write the value back, you'll write the updated value, and you will reinitialize the queue and enqueue the new address that you're writing to this queue. And if you want to do a copy, then you will read this queue until you fetch the value. You will initialize a new queue. So you initialize 2 queues. First to reinitialize the old queue that you just destroyed, and also a new queue for the new pointer that you're creating. And you will append the new address that the value is written to both of these queues. And now this value will hold two tails in it. And now let's say, like, just to reiterate, if I do get twice, maybe on P, then the first time we will append a new address to Q's queue, and the second time we will once again append another address to Q's queue. And finally, to delete a pointer, you just have to dequeue the queue until it's empty, and then make sure that you remove the tail from this value, and then you have deleted the pointer.
I have a question.
Mhm.
Oh, sorry. Where do these queues store? Where are they?
Oh, the queues are also stored on the server. So when we do these, the queues are implemented using write and read instructions, right? So every time you do a write, this value will be written to the server.
So what about the head and tail of the queue? Are they in pointer and pointy, or all of them are?
Yeah, the head will be in the pointer. So here the head of the queue is stored on the pointer, and the tail is stored on the value, but the pointer may also be stored on the server. So if you have a graph, maybe if you have a point, like a pointer to some node in the graph must be on the client, then you can use that pointer to fetch some node in the graph. And then you also, if that node has further edges that come out of it, then all those pointers will also be loaded to the client's memory. And then you can dereference those pointers to fetch more nodes and continue.
Thank you.
Yeah, no problem. Oops. Okay, I think I have too many animations here. Okay, so now let's look at how we can get, I'll give an intuition for how we can get some of our graph algorithms. So there is a slight problem with this smart pointer interface that I have described here, and that is that every value can only store a constant number of tails, right? So that means that every value can only have a constant number of pointers pointing to it. So this smart pointers interface only works if you copy a pointer a constant number of times, or if you want to copy it more than that, you'll have to delete old pointers. So if you want to have, in our paper, we show that you can have more, like a general arbitrary number of pointers pointing to a value. And to do this, we basically organize those pointers as a tree, the inverted tree that points to the value. And we carefully arrange it such that this tree is always balanced. And that's how we get this log D factor in our smart pointer cost. But let's ignore that for now. So assuming that we just have smart pointer interface, which has a constant number of pointers pointing to a value, let's try to see how we can construct our graph algorithms. So let's say we have a graph, and this graph may have arbitrary degrees. So there may be a node that has degree which is maybe n by 2, where n is the total number of nodes in the graph. To be able to perform different graph algorithms on this graph, we first simulate an arbitrary degree graph using a constant degree graph. And I know this looks a bit confusing, but I'll explain what's happening. So these black nodes are basically the same as what nodes were there in the original graph, these black nodes and these black edges. But for all outgoing edges from a node, we will arrange them in a balanced outgoing edges tree, that is this light gray tree here. And for all incoming pointers to a node, we will arrange them in an incoming pointers tree, which is this blue tree here. So this tree has edges in both directions, and it will soon be clear why this needs edges in both directions. And then when we are performing, all four of our graph algorithms can be thought of as a traversal on the graph, where you first fetch a node, then traverse all of its outgoing edges, store them on some data structure, and then one by one, use an outgoing pointer to fetch the next node and traverse that node's outgoing edges, mark that node as visited so that you don't fetch it again, and just continue the graph traversal. So let's see how we can do this traversal. Let's say that we start from node 1. To get all of its outgoing edges, we will traverse this outgoing edges tree. And before that, note that this simulated graph, the number of edges in this graph is a constant times the number of edges in the original graph. And in all our traversal algorithms, we will traverse each of these edges at most twice, which is why the total cost will be E times log E. So yeah, let's say that we start from some node, then we will have to fetch all the outgoing edges. And to that, we'll just do a traversal of this outgoing edges tree. Maybe this could be a small BFS traversal of this tree itself. And all these outgoing pointers, we will store in a stack. The stack will be used for DFS. For BFS, it would be a queue. And for for other algorithms, it could be a min heap or something. Then you will remove a pointer from the stack to fetch the next node that you want to look at. So let's say that that pointer removed is this one in this case. And now using this pointer, you can keep calling get to traverse a path up this tree until you reach the root of this incoming edges tree. And that root is the next node that you want to sort of process. So you'll continue this. So if 3 had some outgoing edges, then you would traverse those outgoing edges and add those to the stack as well. And an important thing that we have to do is in at least BFS, DFS, once you reach a node, you will have to mark it as visited so that you don't read it again. And this is why we need pointers in the opposite direction as well. So we will traverse this tree in the opposite direction by performing some kind of BFS traversal. And we will write in all of these incoming nodes that 3 has been visited. So later, maybe at some other point, if this pointer is popped out of this data structure, we won't traverse up this tree simply because 3 has already been visited and there's no need to visit it again. Is there a question?
Can you just mark a node as visited by like breaking the pointers? By just moving the things? So when I read it, just write it to a new. Never mind.
Okay, I see. So maybe you might move this somewhere else, but then how would you say that this has been, you want to prevent reading 3 from using some other pointer, right?
Good. Yep.
Okay. Yeah, so that's all you'd have to do. You'll have to mark this as visited. And that's broadly how our graph algorithms proceed. So I don't have more than this. I think actually I'm done ahead of time. So if you do have any questions, I'm happy to take them.
Let's say thank you. So you mentioned earlier about like the ORAM lower bound. Is this, can you come up with an analogous lower bound for OSAM? And is this it? Like do we know what an optimum OSAM looks like?
Yeah. So this log n blow up is optimal because using OSAM, you can construct a stack, you can construct queue, and it's been shown in some prior work that every stack operation requires log n blow up. So there's a lower bound for a stack, queue, like all of these data structures that they need log n blow up. And because we achieve that, if you could achieve an OSAM that has better blow up than log n, then you can achieve a stack that has better blow up than log n, and that violates the stack lower bound. So the stack lower bound implies a lower bound for OSAM.
And I guess similar, like, so you're doing like these, right? You're doing everything as like chasing queues. Can you organize those in a tree in a way? And I'm saying this unsurely because I don't actually have an idea, but are queues really the right operation for, or the right
Yeah,
structure?
I think I understand what you're saying. So, well, with the queue, the asymptotic cost you get is this, but with the tree, I don't know if you can get better asymptotics, maybe. So I have sort of like this was one of the ideas that we also had when we were working on this, to maybe um, have this queue as a tree, but it does become more complicated, and we wanted to give a simple solution at least at the start. So
But I guess you're saying, so it may be possible to cut down from D log n, right, to something that's not linear in D, as long as like we don't, okay, so, fine.
let's see. I don't think that we can improve the asymptotic cost even if we change the queue to a tree, but I
Something.
think we can improve constant costs.
But, sorry, so is that proof known? That, hey, like this, the best you can do here is log D log n?
No, I don't think so. Think about it. I don't think there is a known lower bound.
Well, we can talk about this more. I shouldn't use all of your time.
Okay.
Other questions from folks online or in the audience here?
Hi, thank you for your presentation.
Thank you.
Is there actual implementation of these constructions, these algorithms?
No.
Okay.
Majid, we're working on it.
Yeah.
Oh, okay.
So
Okay.
yeah, we're trying. It'll be a couple months at least, but we're working on it.
Okay, that's great. So since you are working with the pointers, yeah, it should be probably low-level languages. For example, working with pointers. Oh, we can simulate them in Python,
Yeah.
but yeah. Okay, got
Yeah, so we're
thanks.
starting in Rust right now, for the actual like OSAM implementation.
Okay, thank you.
I think Rust is quite natural. Like it's just like ownership, you can kind of read the whole bag, validate.
Right.
The operating system.
That was just saying Rust naturally has the semantics where when you read things, they stop existing, right? You have to do copies and yeah.
Okay.
Okay. All right. Why don't we thank Ananya again? Really, I appreciate the time. Thanks very much.
Yeah, thank you. Thank you for this
Thank you
opportunity.
very much.
Yep.
Okay, bye bye. I have a
Thank
class.
you so
Maybe I
much.
will go to the class.